So, let me see if the camera is even. That's fine. We didn't have time to talk about in lecture today is a few things to address some of the confusion surrounding how do I know when something is a pivot? How do I know when something is, I need to get the zeros above it or below it? That's a good question. So what I'm going to do is I'm going to take a step back to the problem that we were working on in class, address those questions, so specifically questions about how the pivots work, how to identify what a pivot is, how to know for certain how to choose which numbers you're able to move down and eliminate. And then from there, that will motivate some definitions, and then we'll talk about the anatomy of these matrices. So there's terminology to go with this procedure. So what we worked on in class is we started with this guy. We started with 0, 3 minus 6, 6, 4 minus 5 on the first row. 3 minus 7, 8 minus 5, 8, 9, and then 3 minus 9, 12, minus 9, what's that right there? Minus 9, 6, and 15. Okay, so this was our augmented matrix. This is what we started with. And then what we talked about in class is we then simplified this down through row operations. So this we found out to be row equivalent to this form 3 minus 7, 8, minus 5, 8, 9, 0, 3, minus 6, 6, 4 minus 5, 0, 0, 0, 0, 1, 4. So I'm going to now address the question, how did I know that I could stop here? How did I know that this was in echelon form? There's a few criteria. The criteria are explicitly all listed in the textbook. So I'll first start with just the intuitive visual idea, and then I will also go and use the text. So first things first, a pivot has to be what we call a leading term. What is a leading term? Well, if I have a matrix, a leading term for each row is going to be the furthest non-zero entry in a row to the left. So if I'm looking at this top row, for example, I'm going to go and search for the leftmost non-zero entry. In this case, if I go all the way, I can go all the way over here and identify that that is the leftmost non-zero entry. Ergo, it is a leading term. On the second row, the furthest, if I go all the way, I run into 0. And that breaks the rule. I'm not allowed to be 0. However, the furthest left that is non-zero is that one. And so this becomes the leading term for that row. What about the next? Well, there's a 0. Disqualified. There's another 0. Disqualified. And you can see pretty quickly I have to scooch all the way across until I end up with the leftmost non-zero term. So we're looking for the leftmost non-zero term per row, and these are what we're calling our leading terms. And these leading terms are what become our pivots. By pivot, and these are the things that we're clearing out and zeroing underneath all of our pivots. Of course, if you're on the bottom row, then you can't zero out. But then what I'm going to do is I'm going to want to zero out on the backward phase everything else that is above or below those pivots or those leading terms. Okay, so that's how I know I can just kind of scooch over these two terms and kind of ignore what's going on here, is because neither of those is a leading term. Neither of these numbers is the leftmost in the row, and so then I can move on once I've isolated that. Okay, so hopefully that provides some clarity for this procedure. So that's how I know what I'm aiming for. I'm aiming for getting a leading term in this very top corner, and then getting my leading terms to stack as in a row as possible. And if something breaks the symmetry, right, it's not a perfect square matrix, then I'm looking for the leftmost, and that becomes the next pivot. So it doesn't have to be ordered. I'll give you, actually, let me write down some examples. So in general, say I had something like 4, 0, 7, 8, and then 0, 0, 9, 9, 0, 0, 0, 1. Okay? If I had something like this right here is a leading term. This right here is a leading term. Why? Because they are the leftmost non-zero entries in their respective row, and then this would be the last one. Okay? So yes, there's that. Think leftmost, non-zero. If you can keep those two things kind of in your head, that's going to help out a lot. Okay, let me grab the textbook. And let me see what page this is on, so if you want to open up your own book. We're in section 1.2. Oh, goodness. Where is this thing? Here we go. Okay. It's page 13 on the 5th edition. So it's basically literally just this box. A rectangular matrix is in echelon form or row echelon form if it has these three properties, okay? All the non-zero rows are above any rows of all zeros, okay? So, for example, that's saying you don't want to have something like this. I wouldn't want to have 0, 0, 1, 2, like this over like 4, 7, 1, 1, 2, 3, 0, 0. Okay, I wouldn't want this. Why would I not want this? Well, it's because I have these zeros above non-zero terms. This 0 should not be above non-zero terms. So this would not count. And that's why we do the interchanges to these swaps, so that I would be swapping rows to make sure that the zeros go all the way down to the sink to the bottom. The second property is that each leading entry of a row is in a column to the right of the leading entry of the row above it. And that's going to give us the staircasing pattern. So notice that the leading entry here is to the left, and then the next leading entry is somewhere to the right of it. And then this one is somewhere to the right, so this actually is fine. However, what we can't have is something like I have like 0, 4, 0, 6, and then I have like 8, 8, 1, 2, and then like 0, 0, 0, 3, okay? So if I look at this, my leading term on the top row is this 4 right here, okay, because that's the leftmost non-zero entry. Only problem is if I go down to the second row, this is the leftmost non-zero entry. Okay, well that's fine and all. The only problem is this is to the left column of the row above it. So in order to get the staircasing pattern, this breaks it. So I need to make adjustments until this is not the case. I can't have the leftmost of a lower row be further to the left than something above it. Okay, so priority is going to go to the top. I want the top to be the leftmost, and then the column. So this fails. You'll notice that this would work because this leading term is furthest to the right. So it's going to be to the right of any other. But if you have one, it breaks it. And then lastly, all entries in a column below a leading entry are zeros. Okay, so that's what we found like here. Here's a leading entry. Below it is zeros. Below it's 0. Same thing up here. All the leading entries below it is 0, unless of course you're on the bottom row. Then reduced echelon is then what we went to, where we proceeded to then simplify so that the leading terms themselves get simplified down to 1. And then there are zeros above, in addition to being below the leading entries. So hopefully that makes sense. The book is very helpful for this, and they actually walk through a bunch of different examples so that you can see. But in general, it will be helpful to think about leftmost. I want leftmost non-zero, and I want those to be the highest up, so that it staircases down nicely. Alrighty. So there are a few things that I wasn't able to get to. First, which we kind of already talked about, we can define some anatomy. So the definition, some anatomy of a matrix. So let's take actually the row reduced echelon form that we just did in class. So we have, let's see, 1, 0, minus 2, 3, 0, minus 24, 0, 1, minus 2, 2, 0, minus 7, 0, 0, 0, 0, 1, 4. Okay. Actually, since this is up, let's go through those criterion again for the row reduced echelon. So first property is that I need to have no 0 rows above this. So you will notice that all of the zeros, so to speak, have sunk to the bottom. I don't have this row of zeros above my other ones. Another thing is when I look at my leading terms, here, here, and here, I notice that they go from left to right. So as I go down in rows, I am not interrupting that flow. So for example, this leading term is in a column to the right of the one above it, which is good. This leading term is in a column that's to the right of the one previously above it. So that staircase as well. It doesn't have to be a perfect square, so long as it follows that behavior. Further, the entries below each of these is 0. So these are zeros, that's 0. And then to make it reduced, all of my leading terms are of the value 1, and above as well as below there are zeros. Okay, so this is row reduced echelon form. Now, these are, so circled, are going to be what we call leading entries, like we've been talking about. So leading entries. And these are the circled numbers. So the numbers that I've circled here, we would call those the leading entries. And then now, let's talk about the pivot positions. And the pivot positions I'm going to box, and they happen to coincide, obviously, with my leading entries when I have it in row reduced echelon form. But think of that box as a placeholder for where that pivot's going to be. How do I identify the pivot? Well, once I organize my numbers in such a way so that they follow those properties that we've talked about for the echelon form, then that's what those locations are. So these are boxed. And then the pivot column, so the pivot columns, I'll also box these, are essentially take a pivot and that entire column is a pivot column. So that right there is a pivot column. This right here is a pivot column. And this right here is a pivot column. Okay. We got to think about what we actually want to interpret this, okay? And that's the key. I'll make a fresh board here and rewrite it. This is kind of the key here, what all of that work actually did, okay? Because when you learn the algorithm, you're like, fantastic, I got it in this form. That was tedious, that's horrible. And then this is why we do it. So we had, just write this down again. Okay, so this is what we were working with. This is an augmented matrix. Of the following system. That's logically equivalent to this system. Let's look at all of these coefficients. There's a 1 here in the position of the first variable. So that means the coefficient of the first variable is 1. So x1. Then there's plus 0 of the next. So plus basically blank 0 x2. Now in the third variable, minus 2 is the coefficient. So minus 2 for that third variable. Then plus 3, the fourth variable. 0 for the last variable. And then that's going to equal my minus 24. So if that, if you need to rewind that and slow it down and play it again, do so. So I'm going to now do the rest. 0x1, 1 times x2, minus 2 times x3, plus 2 x4, plus 0 x5 is equal to minus 7. 0 x1 plus 0 x2 plus 0 x3 plus 0 x4 plus x5 is equal to 4. Okay, so straight away, this augmented matrix produces this. This is a lot easier to read than what we had at the beginning. Recall that the original augmented matrix that we were working with did not look like this. It looked like this. We had 0, 3, 3 minus 7 minus 9 minus 6, 8, 12, 6 minus 5, minus 9, 4, 8, 6, and minus 5, 9, 15. Okay, so this is what we started with. This augmented matrix. Which would have been otherwise equivalent to the system 0x1 plus 3x2 minus 6x3 plus 6x4 plus 4x5 is equal to minus 5. And then the next equation would have been 3x1 minus 7x2 plus 8x3 minus 5x4 plus 8x5 is equal to 9. And the last equation here would have been 3x1 minus 9x2 plus 12x3 minus 9x4 plus 6x5 is equal to 15. So I want you to tell me, if you were presented with this system of linear equations, would you rather see this mess, or would you rather see this? That right there is why we do like this horrible mess of going through all the row reduction. We do all of that because it makes our system much easier to interpret. Okay, so let me erase, I'm going to erase this, and I'm going to show you how we take this and interpret it as a solution set. So how do we interpret this as a solution set? So what we're going to do is we're going to do what's called a parametric description of the solution. So here's our solution set. Solution set. I'm actually going to move this down a little bit. There you go. Okay, so we notice that we have some extra variables. That's okay. We can take the variables that we certainly can isolate. So x1 we can certainly isolate by adding 2x3 and subtracting 3x4, and then we still have the minus 24 hanging out there. What about x2? Well, x2 we can isolate in terms of these other variables by adding 2x3, subtracting 2x4, and we have that minus 7 over there. So then how do we interpret x3 and how do we interpret x4? Because we haven't solved for them. We don't have an equation that can isolate for them. It seems like we can pick a value of x3, and so long as we adjust the value of x4 accordingly, we can still reach a solution. In other words, there's more than just one solution. It's an infinite number of solutions. And so what we do in these cases, whenever you end up with extra baggage on board, we're going to call these free variables. So x3 is free. x4 is free. You might be wondering, well, how do I know? How did I know that, maybe x1 is free and then the other ones are solved for? You can represent your solutions in multiple correct ways. Okay, so there are multiple correct ways to represent these linear solutions. However, in general, follow the pattern of your leading terms. Take the leftmost in each column and then use those. Make all the other ones your free variables. So when I look at this augmented matrix, when it's been row reduced completely, I see, my leading terms here fall on the x1 variable, the x2 variable, and the x5 variable, which means that my other variables are going to be free. So that is a more concrete way that you can kind of determine that. So, what about x5? Well, x5 was just a constant, so 4, it's always going to be 4. In all solutions, x5 will be 4. We call this the parametric description. Parametric description. Of the solution set. Now, we do have a word for the other variables that are not free. So I would say that we have basic variables. We call them basic. Which ones are basic? Well, x1, x2, and x5. Another way to think about that, your basic variables are the variables that correspond with your pivot, your leading terms here in the row-reduced echelon form. And then, of course, we talked about free variables. So free variables are x3 and x4. Now, intuitively, if you have free variables, then there's more than one solution. And like we talked about in the lecture, you only have 3 options. You either have one solution, infinite many solutions, or 0 solutions. Well, the moment we come up with a solution set, we've eliminated the 0 solution possibility. So that leaves us with either one solution or infinitely many. If we have only basic variables, so if suppose all of these were basic, well, that means there's no degree of freedom. And if there's no degree of freedom, logically, that means it's unique. Unique means 1, so then we only have one solution. We have free variables. What does free mean? Well, that means there's going to be more than one option. More than one? Well, the moment you introduce more than one with a linear system, you've now introduced an infinitely many, okay? So in this case, there are infinitely many solutions in our solution set to this system of equations. Okay. So, a few last things. Solving a system amounts to finding a parametric description, like we just did there. Parametric description of the solution set. Of the solution set. Or determining, of course, that the solution set is empty. That the solution set is empty. All that means is you either got solutions or it's zero. Here's a good theorem to know, just conceptually, is that each matrix is row equivalent to only one row or reduced echelon matrix. Kind of think about how when this is a basic example, but when you learn to simplify fractions, the most simplified way you can describe a fraction is unique to that specific simplest form. And then you can have an infinite number of ways to express that same fraction that's not in simplest form, but ultimately there's only those simplest forms are unique. In a similar sense, our reduced echelon matrices, once you row reduce all the way and it follows all those properties, that is an entirely unique row reduced matrix that's going to produce a exactly unique solution set. And then there are an infinite number of different matrices you could have that are row equivalent to it, but all of them can boil down to that one. So that makes every solution set of every single system unique. Okay. We talked a little bit about this on the other one, but now I'll state it as a theorem here. A linear system is consistent if and only if, again, so this is the logically equivalent statement. So if I state that a linear system is consistent, this is going to immediately imply the other thing. The rightmost column of the augmented matrix is not a pivot column. Is not a pivot column. That is an echelon form of the augmented matrix, has no row of the form zero, you have a row of zeros and then like a B at the end, where B itself is a non-zero element. And you might think, okay, that seems like a really redundant thing to say. What on earth is this actually trying to communicate? Imagine you had a matrix, and in the bottom of your row, you had something like a row like this, like 0, 0, 0, 0, 0, 1. And this was your augmented matrix, okay? Really think about what that would communicate. So x1, 0, x1, plus 0, x2, plus 0, x3, plus 0, x4, plus 0, x5. How is 0 plus everything equal to 1? Like, how does that happen? The answer is it doesn't happen. This is a false statement. This is not consistent. This is an inconsistent thing. And so if you end up going through the whole algorithm, so if you take an augmented matrix You make it row reduced echelon form all the way down, and then you get a pivot in that really bottom left corner at the very end. Well, that's a problem. You can't have solutions because you're going to have 0 equaling some number that's not 0. And 0 can never not be 0. Ergo, you can never have a solution. System can't have a solution, so it's inconsistent. So that's what this theorem is really saying. It's if you go through the entire algorithm and you end up with a whole bunch of zeros and then a pivot in that rightmost column, and it's augmented, well, that's a problem. That means we have 0 equals not to 0, and then you have no solutions. So, we could do an example of that real fast. Suppose I had gotten a row-reduced echelon form, 1, 0, 0, 4, and this is the augmented matrix of the system, 0, 1, 0, 3, 0, 0, 0, 2. So we have a row of the form zeros and then some non-zero number. So let's see what that actually produces. If we rewrite this as a system of equations, I would get 1 times x1 plus 0, x1 or x2 plus 0, x3, so that is equal to 4. Then I would get x2 is equal to 3. And then I would get, lastly, 0 is equal to 2. Well, hold on. Really? There's no case. So even though we have a solution for x1 and x2, there's just no way that this works. And so this implies that the original system is inconsistent because there's 0 solutions. It's impossible for there to be solutions. And we could have known that all from just looking here and seeing that the rightmost there's a pivot in the rightmost column. So that could actually get us to that conclusion, just like that. So, last thing, and I'm going to state this theorem as a flowchart. We can say, if I have a linear system that is consistent. Okay, what does consistent mean? Consistent means there's at least one solution. So then we need to ask the question, okay, we have solutions, great. Are there free variables? Are there free variables? And remember that the free variables were the extra ones. The extra ones. That could vary. And if they could vary, well, that means we have infinitely many. So if the answer to our question here is yes, there are free variables, then automatically we can know that there are infinitely many solutions. Just by nature of there being free variables within a consistent system. But if not, the only other logical way to go is that there's one solution. So long as you have a consistent system. So that is the rest. I'm calling it 1.2b, lecture 1.2b. It's the rest of the material from section 1.2 that's important to know, that's going to be helpful to finish the homework and things like that, especially to understand what we're talking about on Friday.